Okay, so let's look at so assignment 7 and 8 solutions are released. So last time we discussed some questions from week 8, some sample questions. So you remember that we discussed this question about non-wasteful NP-free resource allocation. So I did not give you the explicit solution because the deadline was not over. So now that the deadline is over, we can just look at the rest of the solution. So just to recapitulate that we were given a set of items, and there were a set of agents or persons who need to be allocated these items such that every person gets items that he or she likes, and no person is envious of another person. And then the question was that given a fingerprint of an object, an item, so fingerprint, recall that is a set of persons that like an item. So given the fingerprints, we designed an ILP. So the description of the ILP is in the video, and this is a sample solution to the ILP was given. So the variables which were corresponding to a person and a fingerprint was given some assigned values, and the claim was that this is a feasible solution to the ILP, which we have seen in the videos. And the question was, in how many ways uh, this ILP solution could be realized? That means how many different ways to allocate items was there corresponding to this ILP solution. Okay, so the answer is given to be 12. And so there is no explanation to why the answer is 12. So I'll give you the explanation. So let's to the whiteboard maybe. Yeah. Okay, so I'll just tell you how this is 12. So this entry x sub I f is corresponding to the number of items with fingerprint f allotted or allocated to person I. Okay. So here this means that the person 1 is given only one object with fingerprint person 135. So fingerprint person 135 is this. So there are 3 items with this fingerprint. So that means these 3 persons like this item, as well as this item. But out of these 3 items that person 1 likes, only one item has been given to him. Okay. So out of the 2 items of this fingerprint, person 2, 3, 4, none of the items were given to person 1. And person 1 is given the clock. Okay. Because the clock is only liked by the person 1. So there is no choice but to give the clock to the person 1. Okay. So what is the question? The question is, what is the question?
And how to know that that this item has been given to the person 1 only and not to the others? Like say person 1, 3, and 5. Okay, so I mean below it is written that person whether it is given to which person.
So I did not understand the question.
So like here in the very first option, I mean statement it is given person 1, person 3, and person 5 is equal to 1.
Yes.
So out of the 3 items which have got this fingerprint 135, one item is given, but then to
Yes.
whom? But to whom this item is given?
To person 1. That is
And
in the
how
subscript.
Okay, so it is given in the subscript. Fine, fine.
Yes. So how many allocations are possible? That is the question. How many allocations correspond to this assignment? Answer is 12. So I will just write the question also. So how many allocations satisfy this assignment? Answer is 12. And the question is why? Correspond to this assignment. How many allocations correspond to? Let's write that way only. To this assignment. So now, what is the assignment? The assignment is given to you that one of the items with fingerprint 135 is given to person 1. So let us say the camera is given to person 1. So person 1 has got the camera and person 1 has got the clock. So far we are we are in a position to tell that okay, uh, we are just arbitrarily making a choice of the camera. So the camera and the clock is given to person 1. Next we move to person 2. So person 2 gets none of these items. He gets one of these two items. Let us say the guitar is given to him, and of course person 2 doesn't like the clock, so the clock doesn't go to him. Clock has already been allotted to person 1 anyway. So the clock is gone, the guitar is gone, the camera is gone, so we're left to allocate these three items. So person 3 gets what? He gets one of these two. So maybe he gets a mic and nothing else. Person 4 gets what? He gets one of these two. So guitar is already given to person 2. So person 4 gets the notebook. And person 5 is given one of these items. So what is left? The radio is left. So person 5 gets the radio. The question is, in how many ways we could you know, uh, make these allocations
So,
happen?
yeah, so in the case of the first fingerprint, we have got three items. So these three items can be given in how many different ways? Three items can be distributed among three people in how many different ways? Say in six different ways, right? And then there are two items in the fingerprint too. So two items can be distributed in two number of the ways, and then only one item is there for the last fingerprint. So therefore this total number of the ways came out to be 6 into 2 into 1, and I think that maybe because of this the answer is 12, because if we find the sum of the columns here 1 0 1 0 1, so it indicates here total number of the items in this fingerprint. And
Correct.
similarly here also, yeah, so maybe because of this value came out to be 12.
Yes, yes. So basically, so for the clock, there is no choice. Person 1 needs to get the clock. But person 1 can be given either of these three items. So there are three possibilities. Now, once you fix one of the items for person 1 from this fingerprint, then you are left with two choices for person 3 from the same fingerprint. So into 2, and that is 6. And for here also, for this fingerprint also, here the person 2 has two choices here. After that, person 4 doesn't have a choice. Whatever person 2 has been given, the other item has to be given to person 4. So another into 2. So 3 into 2 into 2, that is the total number of ways this matrix of variables assignments can be satisfied. Similar thing what you said.
I could not hear you. What did you say?
Okay,
Uh,
so hello.
yes, yes, audible now. Yeah.
So I am saying that I'm giving a similar argument.
Yes, yes, yes.
The clock is given to person 1 because only person 1 likes the clock.
Mhm.
Now, person 1 is given one of these items we know. So there are three possibilities.
Yes.
And then once one of the items is fixed for person 1 from this list,
Mhm.
for person 3, again person 3 is given one item from this list. Two
Yes.
two choices are left.
Yes.
So 3 into 2, 6 possibilities. Now consider this list. From this list, who all gets these two items? Person 2 gets and person 4 gets. So initially person 4 has choice. He may get the guitar or the notebooks at two possibilities.
Yes.
So once you fix what item has been given to person 2, then for person 4 there is no choice. The remaining item goes to person 4.
Yes. Yes.
So that is how the number of ways is multiplication of these choices. So 3 times 2 times 2. So that's how it is 12.
Yes. Yes.
Okay, so that is just to be complete on what we started last time. So now we can move to the questions of this week 9. This, write it down. So this is week 9 and this is 22nd September. Uh, did we? Okay, so we have to define a few things. Okay, so okay, so let's look at what is called minimum cuts. So consider a graph. So we have a graph G. In a graph G, an x comma y cut is a set S of edges that separates x and y from each other. Okay. So what does that mean? It means that if you remove this set of edges S, so in G minus S, so G minus S is you have removed all the edges from S. There does not exist. There is no x to y path. So that is the definition of a cut. Okay. So we are interested in what is called a minimum cut. So let us take an example.
And X and Y are the set of the vertices or what?
Yes, I didn't say that today. Okay. X, I didn't say this. So X is a subset of the vertices and Y is a subset of the vertices.
Okay.
Okay. So let us take this example. Okay. So let us name them. So these vertices are x1 and x2. This is A, B, C, D, E, and F. And these two are y1 and y2. So let us say x is x1 and x2. And y is y1 comma y2. Okay. Okay. So now consider this cut. So let us say we delete these three edges. So S is AC, BC, and PD. So is S a cut or XY cut? That is the question.
Yes, so this is a cut because the connectivity in between, say, capital X and capital Y is lost. However, instead of removing the three edges, we could have removed simply X1A and then X2B. Then also the connectivity could have been removed.
Yes, that is also true. So this is a cut, but this is not a minimum cut. So a minimum cut is a cut where uh, there is the smallest number of edges that you can remove to disconnect X and Y. If there is no way to remove fewer edges so that X and Y is disconnected, then that kind of a cut is called a minimum cut. For in this case, uh, as you said, if you remove instead of these two edges, that will constitute a minimum cut. Or is it possible to just remove one edge so that X and Y are disconnected?
So if I try to remove only one edge, then still the uh, connectivity would be maintained because I have two paths to make it reversal. So one edge won't be sufficient, I think.
So there are two disjoint paths from say x1 to y. This path is disjoint from x2 to y2. So therefore, you have to remove at least one edge from these two disjoint paths to make sure that X and Y are disconnected.
Yes, and there is a theorem. There is a name for this theorem that the minimum number of the uh, edges required to be removed to make the two things disjoint is equal to the maximum number of the disjoint paths, something like
Yes,
this.
that is called the max flow min cut theorem.
Mhm.
So the max flow is equal to the number of disjoint paths. So in that case, you have a source vertex and a target vertex, and on every edge you have some capacity, and you want to send the maximum flow from the source vertex to the target vertex such that the capacity constraints are satisfied. That means you do not send more flow by an edge than its capacity. And you also have conservation constraints. So you do not, so for example, let us say that the capacity of this edge is 4, the capacity of this edge is 5. So you are not going to send more than 4 flow via this edge. And whatever incoming flow is to a so consider a vertex, whatever is the incoming flow to a vertex, the outgoing flow is equal to the incoming flow. That is the conservation of flow. So with these two constraints that you have to conserve flow at every vertex and you have to respect the capacity of every edge, what is the maximum flow you can send from a given source to a given target? For that question, we solve the max flow mean cut, max flow, we solve the max flow question like that. And the max flow is known to be equal to the mean cut.
Okay.
So yeah, so the reason we are discussing mean cuts is that we are going to discuss something uh, more specific. Okay, so now consider in this graph, this is a mean cut. This is also a mean cut. This is also a mean cut. So we want to distinguish some cuts, mean cuts among these as important cuts. Okay, so let us define what an important cut is. Then we'll move to the questions. So I'll just write it down. An important cut. So in an undirected graph G, okay, let X and Y be subsets of the vertex set, and they are two disjoint sets of vertices. Let S be a subset of the edges so that It's an XY cut. That means if you remove S, then X and Y are disconnected. And let R be the set of vertices reachable from X. Reachable from X in G minus S. So once you remove these vertices in S, so you're left with a residual graph. So in this graph, there are two components, one component containing X and the other component containing Y. So all the vertices that are reachable from X, you call that set as R. And then we say that S is an important XY cut. If it is inclusion wise maximal, that's the first thing. I'll just write it first and we'll discuss what it means. It is a maximal. No, it is inclusion wise minimal. And there does not exist X comma Y cut S dash such that there are at most S mod S edges in S with this thing such that R is a proper subset of R dash, where R dash is the set of vertices reachable from X in G minus S dash. So I'll just use this example. Okay. So in this case, in this example, this is our X and this is our Y. And let us say, so we consider this cut that you have suggested. So you suggested this cut. So let us say S is this two edges. Okay, so let us say S is these two edges. So S is X2A and sorry, X1A and X2B. Okay, so we want to answer the question whether this set S constitutes an important cut. So two things we have to check. First is whether it is inclusion wise minimal. That means, is it possible to get a subset of S and still have a cut? No. So there is this, we already said that minimum two edges are required. So this is definitely inclusion wise minimal.
Yes, but I am doubtful about this thing. That what this R here is that R be the set of the vertices reachable from X in G minus S. So if I remove these two edges from the graph, then graph
Yes.
will become disconnected. So if
Yes.
the graph becomes a disconnected, then what this R comprises of then, and where is the issue of the reachability arises then?
Okay. So now once we have deleted these two edges, we
Uh-huh.
have been able to disconnect X from Y. Okay. So now what is
Right.
the connected component of X? The connected component of X is only this one edge. But the connected component of XY, that means the set of, so see, this is one connected component. All these vertices are reachable from each other. This is one connected component. This is another connected component. Now we are saying that we are asking, we are defining R to be the set of vertices that are reachable from X1 and X2. That is X. So in this case, the set of vertices reachable from x1 and x2 is only x1 and x2. So R is only x1 and x2. Correct.
Okay, yeah. So fine. So, so it shows that in every case, the R will comprise of only the vertices of the set X only, and no vertex of the set Y will participate in the set R.
That we'll see. That may or may not be true, but let us see. So first, let us decide. Yeah, go ahead.
Yes. Okay, so because I right now I cannot visualize that how
Yes,
can
yes,
this
yes,
happen, because D minus S would be completely, I mean, disconnected graph. Uh,
yes.
and yeah,
So R will probably be expandable beyond x, but let us see.
okay.
So first thing
And
is, yes.
yes, please continue. Yeah.
So to decide whether this is a minimal cut. So first thing is, first condition for being important cut is satisfied, that it is inclusion wise minimal. Then we want to check that whether there exists another xy cut is dash with two or less number of edges. So modus is how much? Modus is 2. So whether there exists another xy cut is dash with two or less number of edges. Less is not possible, we already said, because there are two disjoint paths connecting two vertices from x and y. So let us try to seek an xy cut with two edges, let us say s dash, such that R dash is the set of vertices reachable from x in G minus S dash. So if you remove the edges from S dash, whatever graph you will have, in that graph, R dash is the set of edges reachable from X. And R dash is also a superset of R. Okay. So does there exist such a cut? That is the question. If there is such a cut, then we cannot mark S as an important cut. Otherwise, we'll say that yes, S is an important cut. So which one is S? This is not S. This is S.
So here the equality is also the part of this, no? So the cardinality of S dash could be equal to the
Yes.
cardinality of X.
Yes. Need not be strictly less. Can be
Uh-huh.
equal also.
But then this R dash should contain R. It is a
Yes.
requirement.
So here what
Okay.
is R? R is nothing but X. So R is X in this case. So can you think of expanding R and getting a XY cut? That is the question.
Yes, I can. Rather, I can remove this EX1 and then FX2 here. So at least my X will get expanded.
These two,
Yes.
EY1 and EY2, right? Yeah, so consider this. Consider this set of vertices as R dash. Okay. Now, if this is R dash, then what are the uh, so this is R dash means from X and Y, from X1 and X2, all these vertices are reachable, and the edges which are going across R dash, that means these two edges, are in fact the cut edges. So
Yeah. Yes.
EY1 and FY2 consists XY cut. So that is the S dash. So consider S dash to be these two edges, EY1 and FY2. This is a valid cut, XY cut. And also, if you remove these two edges, so the component containing X is this one. And in this component, all the vertices are reachable from X1 and X2. So R dash is a superset of R. So initially R was X, now R is these two as well as all these vertices. So therefore, we have found a S dash which respects this property, and therefore we can conclude that S is not an important cut. But what is the status of S dash? Is S dash an important cut? So
Okay,
it is,
okay. So S dash would be an important cut if I cannot expand. I mean, if I cannot expand, uh,
yes,
if I cannot expand X further. So yeah. So if R is so now this time R dash comprises of so many elements, and only two elements are remaining, which are not the part of
yes,
the R dash.
yes,
And yeah, so uh, yes, so R dash is an important cut. Clearly, I
yes,
cannot expand it further.
yes. So there is only two vertices left, and those two are supposed to be disconnected anyway from R dash. Those are y1 and y2. So there is no way to expand R or R
Yes,
dash in this case. So the S dash and corresponding R dash are important. So we have got an example where we can identify or we have illustrated how to identify an important cut. So out of the minimal cut, some of the cuts are important, some of the cuts are not important. It depends on whether the component containing the X part of the cut is expandable. So,
yes,
so now what about, so see the definition is such that the definition is not symmetric. So X, see an XY cut. So let me just go down and take a fresh page. So consider an XY cut. So an XY cut by definition is a set of edges that disconnected X from Y. So an XY cut is definitely equivalent to an YX cut. So whatever is set of edges that disconnects X from Y also disconnects Y from X.
yes. Only for undirected graphs then.
Yes. We're talking for undirected graphs only right now.
Okay.
But what about an XY important cut? Is this equivalent? Asking the question to an YX important cut. Remember, the important definition is with respect to the component where y is lying. I mean, the first part is lying.
In case of XY, clearly we would be having those vertices which are the part of the X. I assume that once we found the cut, then the connectivity between X and Y is lost, and say this R
Yes,
would only comprised of the vertices taken from the set capital X. But in this reverse direction, I would be only having so R would only be having the vertices which are the part of the set Y and not of the X clearly. So therefore, this is not symmetric. The cut could be
yes,
symmetric, but then important cuts need not to be symmetric.
that is right. So you have got the right answer. So this is not true because in this case we have seen that an important XY cut would be to remove these two edges. But equivalently, we see that an important YX cut would be to remove these two edges because the component corresponding to Y is as large as possible if we remove the edges x1a and x2b. So therefore, the important cut for x comma y is not same as the important cut for y comma x.
Yes.
Okay, now we can go to the questions. Okay, we have the pages. Let's pick the questions. This is the one. This is not the one. Yes, this is one. Okay, fine. Okay, we'll start with the first one. We want to decide which one is true, which one is false.
Yes. So the first one say that every XY cut has a subset that is inclusion wise minimal. So every XY cut has a subset. So so can we consider that every set is a subset of itself? So then it is
Yes.
true that yeah, so quite possible that the XY itself is minimum. Otherwise, we can find a minimum one. So A seems to be true.
Okay. So yes. So the thing is, if x comma y is a cut, that means let us say that this is x and this is the component of x and this is y, this is the component of y, and some edges are going between the component of x and the component of y, and therefore if you remove these edges, then x and y will become disconnected. So if it is a cut, then for sure it is able to disconnect x and y, but whether it is a minimal cut or not, that we do not know. But definitely that if it is not the minimal cut, then some of the edges can be removed from this minimal cut to make it from this not minimal cut to make it a minimal cut, because disconnectivity is already achieved. Once we are saying that x comma y is a cut, that means the set of edges in x comma y cut is already disconnected x and y, but maybe it is not minimal. So maybe there are edges which are redundant and can be removed, and still the disconnectivity will hold true. So therefore, it is always the case that a subset of any xy cut will be inclusion wise minimal. Does that make sense? Or do you have any?
Yes, yes.
Yeah, I mean, so for example, I'll just take a small example. Let us say that this is again that example x1, x2. And let us say, just making it simple, y1, y2. So this is our x, this is our y. So this is, if you cut this and you cut this and you also cut this is a valid cut.
Yes.
This is not a minimal cut because this was not necessary to remove. But you can always take a subset of this cut to get a minimal cut.
Yes.
This is true. Let me mark it true.
And second option, we have just discussed that a minimal XY, just now you told that it is symmetric.
Yes,
So, so therefore this is true. B is also true. And C is not true. It is false because this is the case of the important cuts. And every important cut is a minimal cut. Every important cut is a clearly it has to be, it should be true.
that is the
And
table.
every minimal cut is an important cut. This is not necessary, and we saw this in case of
Example.
X. Yeah, in the example. So this is false.
Okay. So got everything right. Let's move to the next question. So consider XY cut. Let S be an important XY cut in G. So we have this setup. That there is X. Yeah.
Yes, yes, please, please.
There is Y. There is some vertices which are reachable from X and some vertices which are reachable from Y after you have removed the cut edges. Okay. So this is R. and R is not expandable. So this is S. So because R is not expandable and S is a minimal cut, therefore it is also an important cut. Now we are asking that, okay, if you remove one of the edges from S, let us say we remove one of these edges, maybe you just remove this. So S minus E, is it also an important cut for G minus E for this graph? Not continuing.
Okay. So yeah, so basically they are transforming the graph by removing this edge. And I mean, they say that the set S minus E for every edge, E is also an import. So if I remove this E from here, if I remove this edge, and so will this be an important cut? So if I remove this edge, uh, I mean, extension is not possible. It cannot be. I mean, if I remove something, then by using that thing, the extension is not possible. So therefore, uh, the G minus E would still remain disconnected, and
Yes.
that will comprise of the minimum number of the edges as well. So therefore, to me, it seems that this is true. This is true option.
Okay. So formally we have to check two things. We have to check two things in G minus E. First is whether S minus E is a minimal cut, inclusion wise minimal cut in G minus E. That is what we have to check. That is the first check.
So, but S is an important cut, so therefore it has to be the minimal one only. So,
Yes. So because S is an important cut, it is also a minimal inclusion wise minimal cut in G. And because we're just removing an edge, so see, there is no way to remove an edge and still maintain the disconnectivity of X and Y in this graph. So if we remove an edge, so X and Y will become connected. Yeah. Sorry,
uh,
what am I saying? Just a
so
second.
yeah.
So if I remove an edge, for example, this is the case. If I remove an edge, so yeah, I can write. But go ahead.
Yes. I could not. So can you repeat this statement which you made just now?
No, so I am saying that because S is an important cut, it is also an inclusion-wise minimal cut. That means whatever the edges are there in S, they form a minimal cut. That means if you remove even one of these edges, and if you just say that, okay, I am going to declare that these edges, not this one, what, so one less than mod S edges eh, forms a minimal cut, then that is not true, right?
Yes.
So because that by definition it's a minimal cut. But then we are asking that, okay, that is fine, but in G minus E, in G minus E, whether S minus E is a minimal cut. Okay, so we know that S minus E is uh, not even a cut, not even a cut in G, but is S minus E a minimal cut in G minus E? You
So
understand what I'm saying?
yes. I understood this point. And so this S minus E is not an important cut, is not a minimal cut, say, for the graph G. Because if I remove G, if I remove one
Yes.
more edge, then it shows that clearly that cut is not minimal. So I mean so if I remove one more edge, so actually this is getting confusing because S minus E, because this S minus E, yes. So if I remove one more edge from here, then clearly this is S is a set of the edges which need to be removed. So if I remove one edge from the S, so will it be an important cut for the graph G minus E. So, yeah. So
First answer, let us try to answer this question, that whether S minus E is even a minimal cut in G minus E. So whether it is disconnecting. First, whether is S minus is going to disconnect X and Y in G minus E.
okay, so if I view this question in reverse, that since so the negation of the G minus E is the negation of S minus E. No, not in that way, contrapositive way, that won't work here. So if S is the minimal cut of the G, then if I remove one more H from here, one H from this S, then it is not necessary. I think that this would be, because it depends on the interdynamics of the connectivity in between X and Y.
Okay.
So quite possible that so the cardinality would be, it may be possible that the cardinality of S minus 1 would be
Mhm.
the minimal cut of the G minus E. But it is
Okay.
not necessary that that age has to be E only.
I see.
Quite possible that because of the interdynamics of X and Y, even if you remove E, then some of the connectivity may remain maintained.
Okay. Okay. Fine. So I understand what you're saying. You're saying that okay, I do not know what if S minus E is a cut or not, but there is a cut of size mod S minus 1 in G minus E. That's what you're saying.
Yes, yes, yes.
Okay. So let's try to revisit what we just said. So we said that okay, because S is an important cut, so it is also a minimal cut. That means through each of these edges, you should be able to find. So each of these edge in the cut forms part of distinct paths between X and Y, vertices of X and Y. Correct?
Yes.
So that means even if you do not remove one of the edges from S, then you won't be able to disconnect X from Y.
Uh, Please say again.
So I'm saying that if you do not remove, even if you do not remove one of the edges in S, then at that the path, so if you do not remove an edge E, which is an S, path, the path connecting X and Y via E will still remain, and therefore X and Y
Yes.
will not get disconnected.
Yes, yes. Connectivity would still be maintained. Yeah.
Yes, now we are saying that look, this edge is not there at all in the graph. So okay, so let us say just let us fix an edge. So let us say this is an edge. So this is E. This is E, and we are asking that. So we have this graph, new graph G minus E. So in this new graph G minus E, that path which used to exist connecting X and Y via E is no more there. So
Mhm.
this edge is not there in the graph at all. So this edge does not contribute in any way for disconnecting X and Y.
Okay.
The edges which are responsible for connecting X and Y are the rest of the edges only in the graph G minus E.
Yes. So in that case, yeah. So now it's clear that this would be a true then, because
Yes.
if
So this is a cut for sure that S minus is going to be able to disconnect X from Y. But is this a minimal cut or is there a smaller cut? Is it possible that maybe maybe we delete this edge and we claim that rest of the edges is cut for X and Y? Is that true in G minus E?
so, yeah. So whatever is true for E would be true for the other edges as well.
Yes, yes, yes. So we have established
So
that S
like say
minus
if
A
we
is a
consider
cut.
another age say f, then I mean s minus f uh,
Would be a cut. The S minus F would be able to disconnect X and Y in G minus F. Okay. I think you have muted
I
yourself.
do not know whether I got disconnected or you got disconnected.
I don't know. I thought that you inadvertently muted yourself.
No, no, no. But I got disconnected. Suddenly it said that
Okay.
something went wrong with the
Okay.
meeting and we will reconnect you soon.
Okay. Okay. I think there's a network issue. Right.
Yes.
So we were saying that we have been able to establish that S minus C is definitely a cut in G minus C. But now we want
Yes.
to ask whether it's a minimal cut or there is a smaller cut than the size of S minus C. But if there is a smaller cut, then what would happen? Then there would be a smaller cut than S in G, right? So let us say
Yes.
that the cut size in G is 5. Let us say this is the 5 edges only, and the minimum cut size in G is 5. So S mod S is 5, let us say. So now in G minus C, mod S, if G minus C has a cut of size 3, then what does that mean? Then you add E with this, you add with that would be a cut of size 4 in G, and that is a contradiction. So if the size of the minimal cut in G is mod S, then the size of the minimal cut in G minus C would be mod S minus 1, that is 4. So this is not only a cut, this is also a minimal cut.
Yes.
That makes sense, right? I think you have muted yourself.
Yes, this is correct. Yeah,
Oh,
this is right.
all right, all right. So that means that we have convinced ourselves that the set S minus C for every edge in the cut is also an important cut for G minus C. So that we can mark as true. Okay, let's move to the next one. Wait, just make some space. So you're able to see the second question so far now.
Yes, yes, visible.
So if S is an X dash comma Y cut for some X dash that contains X, then S is also an important X dash Y cut. So now it is saying that look, X dash Y is a cut that contains X, but the claim is it is an important X dash Y cut.
So this question does not make much sense because in both the sides they have given x dash only. So if S is an x dash y cut, so it is not necessary that it would be an important cut as well. So this is not necessary. However, it is not clear that I
There is a
mean,
typo. Yeah, yeah, yeah. So there looks like there is a typo. See, if S is an so there's the claim is if S is an X dash Y cut, then it is also an important. That makes zero sense. Uh, so what would okay? This is actually a typo. Maybe the original question, the intended question would be if S is an X dash Y cut. So let me just draw this. Let us say that there is a set X dash which contains X and X dash S is an X dash Y cut for some X dash. Then S is also important dash xy cut. Is it talking about xy cut? Or maybe just we'll just park. We don't know what is the intended question of the question designer. So I'll just keep it holding for now. Okay, so delta R, we you have not seen. So let me define delta R. So delta R is the set of edges in G where, okay, I should define it this way. So delta R is a set of edges in G such that each of these edges, each of these edges has one endpoint in R. So this is similar to being a cut. So consider this is R. So delta R is all the edges which are going out of R. One endpoint in R, the other endpoint is outside of R. So these are the edges, the cut edges basically. Okay.
Okay. So can you repeat the definition of the delta? Is this
So
the
delta R is the, so consider in a set of vertices R. So all the edges which are going out of R, one endpoint is inside R, the other endpoint is outside of R. The
okay?
cut
Okay.
edges. Those are
So,
the edges in delta R.
okay. So would it be same as the cardinality of the cut?
Yes, yes, right.
Okay.
So delta R is a minimum XY cut, then delta R is delta this, and it is also a minimum B comma A cut. That is the claim. So take a moment to digest this.
So VG minus R stands for that all the vertices of the graph
Yes,
excluding the vertices which are the part of the X in this case. So this comes out to be say the Y only, then this is the delta of Y. So they mean to say that if delta R is minimum, then the delta of R, which is the cardinality of this thing, delta R, okay, the number of edges emanating from the vertices in R is same as what? Same as the delta of
the rest
the
of the
Y,
vertices.
delta
Yes,
of Y. So all
not
the
Y.
vertices.
Y is just, let us say, Y is just set of vertices. Maybe other vertices are there. So R and rest of the vertices. So VG minus R is the rest of the vertices in the graph. So maybe there are
Yes,
other components are also there. We do not know. So in that case, this is R and this is V minus R.
this is V minus R. Yes, so but then they say that if both are equal, so it shows that this will also be a minimum B comma A cut, which seems true to me, which seems correct to me because
Yes, yes, this is correct. So this is just simply saying that look, there is a cut. One side of the cut is R, the other side of the cut is the rest of the world.
yes,
So if it is a minimum cut for, because this is an undirected graph, it is not
yes,
claiming anything about being important cut. It is only talking about being a minimum cut.
yes,
So it is like viewing it from one side or viewing it from the other side, you are going to get a cut anyway.
yes.
Let us mark it too. So the next one is just negating what we just established to
Yes.
be true.
Yeah, it has to be false then.
Okay, now if delta A, that means the cut edges out of A and the cut edges out of B are both XY cuts, then so are the cut edges out of A intersection B and out of A. So let's do one thing. Let's draw the right diagram. Let us say this is A and A and B are overlapping. So this is A intersection B. Okay. So now it's saying that delta A, the edges out of A, this is sufficient. This is required. This is not. This is not required. So three types of edges are possible that are going out of A, right? One is its endpoint is in A minus B. This one. So this part is A minus B. This part is A intersection B, and this part is B minus A. Yes.
Yes. So even though this figure is not that much clear to me, which you draw here, but I could understand something from this figure is that if delta A and delta B both are XY cuts, and so if both are, I mean that so the cardinality of the delta A could differ from the cardinality of the delta B. But then and because they need not to be the minimum cuts,
Yes.
so their cardinalities may differ. So if their cardinality differ, then it is not necessary that their intersection would still be a cut. However, their union will definitely be a cut. So
Okay.
if you remove more number of the edges, then clearly it is going to be a cut.
Okay. So let's try to see. Okay. First, the figure is not clear, so I have not elaborated what I mean by these edges. So consider delta A first. So delta A is nothing but the set of edges in the graph such that each of these edges has one endpoint in A. So this is A. One endpoint in A, other endpoint is outside of A. One endpoint in A, the other endpoint in B minus A, this part. One endpoint in A, the other endpoint in B minus A, and that's all. Is there any other possibility? So I'm just saying that there are three different types of cut edges out of A, right?
Yes.
And we want to argue that delta, first you said that it is clear to you that delta A is a cut, is XY cut, and delta B is XY cut immediately implies that delta A union B is also an XY cut. So let us see. So what are the types of edges out of A union B? So anything between A and B is not allowed. So this kind of edges out of B or out of A or out of A intersection B, right? So you are
Yes.
saying that delta union B is immediately an XY cut for you. Uh, how do you justify that?
So if delta A is the XY cut, and I mean, this figure is clear to me now. So if delta A is XY cut, then delta A, so we are basically interested in X and Y part only. So
Yes.
there could be edges which are going away from A. But then those edges which are going from away from A should go towards Y. Uh, so, and in fact, all the edges which are going towards Y only matter to us. And so therefore, I mean, those edges which are going away from A in different directions won't matter to us. So yeah, so clearly delta A. So if I remove the ages which are emanating from A, so I mean this is yeah, this is justifiable because all the ages which are emanating from the set A are going to disconnect X and Y, and all the
Yes.
edges that are emanating from B are also going to disconnect X and Y. So clearly, if I take the union of A and B,
Mm-hmm.
if A and B alone are disconnecting X and Y, so their union will definitely disconnect X and Y. There is an issue in this.
No, so delta, if you say that, okay, delta U A union delta B will disconnect X and Y, that I understand.
Ah, okay, okay, fine.
But our question is, does delta A union B disconnect X and Y? So delta A union B need not be same as delta A union delta B. Is that right?
But uh, why will they differ, by the way?
Consider this edge. It is in delta A as well as delta B. It is going outside of A, and from the B's direction, it is going outside of B. But it is not going outside of A union B. Is it right?
Yes, yes, yeah, yes, right.
So I think maybe it is already 7:15. We didn't take the break today. So maybe you give
Yes,
it a
yes, sure,
thought. You can take a break and resume after 5 minutes.
sure, sure. Shivang has also joined, by the way.
Oh, great. Am I audible?
Yes, yes.
Okay. So, before the break, we were discussing that although delta A is a cut for x comma y, and delta B is a cut for x comma y, uh, delta A union B may not include all the cut edges of delta A union delta B. So, is it still possible that delta A union B disconnects x and y? So, what do you think?
So yeah, so most probably say A would be disconnecting X and Y from A would be disconnecting X and Y. Yeah, so different directions are not possible. So
So, let's try to visualize things with a diagram. So A is able to disconnect x from y, that we know, that is given to us. So let us say that this is A and x is inside A and y is here, and this is some vertices, rest of the vertices, the other component, and the edges going out of A are forming a xy cut. Okay. On the other hand, B is also an xy cut. So B also contains x. Okay. So B is like this. So maybe I should draw x slightly smaller. Then I will be able to draw it properly. So this is x. B is here. This is B. All right. And the edges out of B, let's use a different color. Maybe what is it? Red color. So edges out of B. So this is an edge which is out of B. This is an edge. Maybe there are other edges. Okay. Yeah. Yeah. We also form a cut. Now you have a better picture.
yes, so but then can we really have different ages? Because even from this figure, I mean, all the ages need to be broken down to make X and Y disconnected.
No, no, no.
So
See, why? For example, these two edges, they need not be disconnected. If you're taking these three red guys, then X is disconnected from Y, isn't it? This is strictly away. So this is not even. So you want so what I mean to say, there is a path. See, if you are considering the XY cut with respect to A, then there is a path like this. There is a path like this. I understand. So this needs to be disconnected. The three things will disconnect. But it is also possible. No, no, no. So what I'm saying is wrong. Okay, so if you just disconnect this, then this path still remains, right? Okay, sorry, sorry. So you were saying that all these things have to be anyway disconnected.
yes, should be disconnected. And so where the question of this minimal cut then arises then, because we have to find the minimum number of. So okay, so yeah, so basically we have to break all the possibilities in between X and Y. All the bridges need to be broken down. Yes.
So X and Y are, so we are considering XY cuts need not be minimal. Check if there is any question. Okay. Obviously, I did not. I have to think about it. So the answer, what is your guess for the answer? Is this true or false?
Yeah, so because now after this discussion, I have even this doubt that the elements of the delta of A and the elements of the delta of B both would be same, because I mean even we cannot have, so yes,
Oh,
because they
okay.
are the cuts, because they are the cuts and not the minimal cuts. So had they been the minimal cuts, then delta A would have been same as delta B. So now in this case, delta A and delta B may differ in the sense that delta A could be a cut and delta B could be a minimum cut.
Yes, yes, yes. So they
That
were,
that could be one of the possibility.
yes. So we're not claiming that the cut is minimal.
Yes. So if one is cut and other one is minimal cut, then only their elements may differ. Otherwise, their elements would be same. Uh, Now I think so. And so therefore, delta A intersection B will result into what? Into the edges which are common to A and B. So this commonality may not make X and Y disconnected. However, if we take the union, then basically the union of delta of A union B would either be equals to delta A or would be equals to delta B, depending upon which one is the cut and which one is the minimal cut. So therefore, this will definitely be a cut. This is, I mean, initial perception.
Yeah. So you have confidence that delta A union B is going to be a cut.
Yes, yes, according,
Yes,
because
yes,
we
yes,
need to make the things
yes.
disconnected. Yeah.
So we are cutting everything away. So right. So delta union B meaning that okay. So out of this entire set of vertices, whatever is going out, maybe some of the vertices are going like this. Those things are also cut, but along with them, these things are also cut.
Yes, yes,
So definitely we are able to disconnect X and Y.
yes.
So we have this thing is a cut, XY cut. This is right. So let us argue about A intersection B.
So in A intersection B case, quite possible that A could be a cut and B is a minimal cut. So then intersection of A and B would then carry, so in any case, yes, yes, yes. So even now this A intersection B would also be a cut. Why so? Because all these, all these bridges. So if I find the common elements, so delta of A intersection B here would be equals to the minimal one, whichever is minimal out of these delta A and delta B. So therefore, this will also be a cut. So both are true. Both are true.
Okay. So you're saying that just disconnecting these two guys will be sufficient.
So my point here is that if I take the intersection of delta A intersection B, so the intersection can never be these two guys only. I mean, the intersection will always be all the bridges which are connecting X and Y.
So if so, this is the intersection B, the one that I have highlighted, and delta A intersection B is all the edges out of this region. Now, if this edge is still there, uh, so you're saying such an edge cannot exist.
So actually, at this point, I thought of this delta A intersection B as so yeah. So this delta, I did not think in this way.
Okay.
So I thought that the intersection of A intersection B is all the A in so I mean, but this interpretation is correct. So therefore, quite possible that A would be, but no, such a situation can never arise. That we have a partial overlapping. We would be having either B is completely inside A or A is completely inside B. That's it. I mean, these are the only two possibilities. in my discussion. I cannot have such a scenario wherein there is a partial overlap.
So you're saying B minus A is empty and A minus B is also empty.
Yes, yes, yes.
No, no. So you're saying one of these things is empty. Okay. Okay. So why are you saying that?
Yes, because my assumption is that either delta A and delta B both are same, or they can differ only when either delta A is a cut and delta B is a minimal cut, or delta B is a cut and delta A is a minimal cut. That's it. Then only they can differ. Otherwise, they cannot differ.
Okay. So a vertex here as well as vertex here is not possible. That's what you're saying. So let us say that what you are saying is true. Let us say I just change A. A is this. B is contained in A. B is this. This one is B. All right. So A intersection B is entirely B. And therefore, because delta B is a cut, so intersection B is also a cut. So these edges are probably not like this. So these edges are probably outside, not cut edges. Okay, so I'm not yet convinced. So let me try to see if I can give a more concrete argument why. So this answer is true. So this is marked as true. So let me try to see if I can give a concrete argument in favor of why delta I intersection B should be a cut. Okay. Okay, makes sense. Makes sense. So I'm just speaking aloud what I'm thinking. So since delta is a cut, so if there are cut edges that are emanating from the region A minus B and going into this region, since delta B is also a cut, and if those edges are there and those edges are not part of delta B, then the fact that delta B is a cut itself is getting violated.
Yes.
So if there exists an edge which is strictly outside of B but inside of A minus B, I mean, if there is a vertex which is in A minus B and there is an edge which is a cut edge connecting X and Y, then that edge is not part of delta B, and therefore the fact that delta B is a cut itself is a violation. It's getting violated. So what you were saying is correct. So that means all the edges which are cut edges out of delta A, I mean from this region, delta A minus B, are not the disconnecting edges, these kind of edges. So all the disconnecting edges are basically emanating from intersection B only. So
Yes.
maybe it is not true that A intersection B So A is contained in B or B is contained in A, that I'm not convinced. But maybe there are cartages. Maybe B and A are like this only, that A intersection B is some portion. So maybe there is some portion
Yes.
of B outside of A, there is some portion of A outside of B.
Yes.
But
And whatever is emanating from A minus B and B minus A, these all are the extra edges, right? And
yes.
are not the part of the minimum cut.
Yes. There are cut edges, but not minimum cut edges, but those edges which are part of minimum cut edges, those are emanating from A intersection B only. Otherwise, the fact that delta B is a cut and delta A is a cut itself is getting violated. So that is the
Yes.
reason we will have all the cut edges emanating from A intersection B. Therefore, delta A intersection B is also going to be a valid cut.
Yes.
Okay, maybe this discussion was necessary to come to the conclusion. But it has taken a bit of time. So anyway, so we'll mark it true. So I think we have time for one other question. So let's take another question. So generally 2 hours is a very long time, but I am sure
Yes,
that
true.
oh, I am see, I am going to go by the policies only, so I have to anyway conduct this for 2 hours. Okay, so here is a definition. The definition is of that of a submodular function. You are able to see the entire box, right?
Yes, visible.
So, so this is defined over all the vertices of a graph. It need not say for submodular function, the submodular function need not be defined over the vertices of a graph. It can be defined over a set. So here the set is the vertices of the graphs, and you are considering the power set of the vertices of the graph, and the function is defined on every set on the of the power set, and it assigns a real number r to every subset of the vertex set. Okay, so we call it submodular if it satisfies this inequality. That again, this is A, this is B. The value of the function for A plus the value of the function for B is at least the value of the function for intersection B plus the value of the function for A union B. So that is the definition of a submodular function. And submodular functions are very well studied, nice, and it has many applications in many theoretical computer science problems. So here we're going to see some properties of submodular functions. In fact, this would also require some, discussion and brainstorming. Yeah, so we set out to decide the first one. So if f is a submodular function and it is also symmetric, symmetric means this, that the function value at a particular set is equal to the function value at its complement. So that is the definition of symmetric.
So, what's the meaning of the term in this inequality? What's the meaning of f of a? So, is this the real value assigned
Yes,
to what? To all
A
possible subsets of a or what?
to A. So for example, let us say this is our graph. This is, let us say, B1, or just we may call it ABCD. ABCD. So you are going to, so consider any subset of the vertices. Let us say A is equal to A comma B and B is equal to A comma C, or let's say A comma C comma D. Okay. So
Mhm.
f of A has a particular value. So let us say f of A is, I don't know, maybe 0.53. And f of
Hmm.
B has a particular value. Let us say 1.2.
Hmm.
So what is A intersection B?
So it is a only. Huh.
Yes. So let us say it has some value. So how much is, I don't know, maybe 0.6. And f of a1 and b, maybe 0.6 is too large a number. A1 and b is everything together. So f of a1 and b, let us say, I don't know, 6, 1. That is, so we can make it like, okay, fine.
So
Let's make it.
is it possible that the function value of A is bigger than the function value of the union of A with something else?
Is it possible that the function value for a is bigger than the function value of a union b? Is that the question?
Yes, yes.
So nothing is stopping that from happening. As long as this inequality is true, nothing is stopping. So maybe we'll take an example. So let's say that this is 1.5. So a union b is, let us say, 0.9. Okay, so what is fa plus fb? Fa plus fb is, the left hand side is 1.7.
2.7, yeah.
Oh, sorry, 2.7. It has to be greater than 0.4 plus 0. As long as this is true, we don't mind.
Okay.
But it has to be true. This inequality needs to be true for every a comma b.
Haha. So function values would be assigned in this fashion only, yeah.
Yes. So for a vertex set of size 4, there are 2 to the power 4 functions for each of these function subsets. For each of these subsets, this function is assigning some value, and the values are assigned in such a way that for every pair a comma b of subsets, this inequality holds true. So we can do some manipulations. So we want to prove that fa plus fb is at least fa minus b plus fb minus a. So with the condition that this is true, we
Yes,
either
so
prove this or we
yeah,
prove this. So we do not know. If this is true, then this is false. If this is false, then this is true. The negation
right.
of the other.
Yes. So like in this case, say if the function value of A plus the function value of B is greater than the function value of A minus B. So function value of A that does not contain the element B, and the function value of B that does not contain the value A.
Yes.
Right. So yeah, and f is a submodular function.
Yes. It's a submodular function.
So yeah. So yeah. So submodular function. So I don't understand. But then from this inequality, I came to know that in this inequality, the left hand side is say the FA, so area covered by this circle A plus the area covered by this circle B. So basically, intersection has been counted twice here, and so this is greater than what? The f of intersection of A union B. Yani ki this, so here also in the right hand side also, I
Correct.
have counted this intersection area twice.
Yes.
So, following this observation, the first one is clearly true. This
Okay.
seems true to me.
Yes. So this is a clever way of arguing, but this is not the formal argument. But I think this would be a I don't know, quick way of making conclusions. So you are talking in terms of cardinality. You are saying that, okay, if I consider f to be the cardinality of a set, then this is true for cardinality. So if the function f is nothing but the cardinality, then this is holding true. Then you are saying that, okay, the cardinality of a plus cardinality of b has to be at least the cardinality of a minus b and b minus a. But f is not the cardinality. So we have to give something more generic, more general argument.
Okay.
But do you understand? For
Yes.
cardinality, what you were saying is right.
Yes. 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 It's fine. It's fine. Yeah.
Let us do one thing. So let us try to write something for if. So we know that, so this part is a minus b, and this part is b minus a. Okay. Now f of a plus, sorry, let's take the pen. Let's take red. Red is also blue. Let f of a minus b plus f of b minus a. This is greater than equal to, what is intersection of these two things? Is f of phi, and f of a union.
F of a this is, yeah, this so the union of these two will be the f of a union b minus a intersection b.
Yes. So we have something on uh, something of this form. So we want to say, okay, our goal is to make prove that this is true. That's our goal.
Yeah, so so instead of f of a, let us consider, say, f of a not b here in this inequality,
Okay.
in this original inequality only. Let us put
Yeah,
the value, replace,
yes.
yeah, here, yeah. Let us replace a by a not b, a minus b.
Okay.
So if this is a minus b, then what is the intersection of a minus b with b? That value will come out to be phi. And what is the union of a minus b with b then? With this entire b. So this a minus b and this its union with b, what do you think would be equals to the a union b itself?
Yes.
And so probably we can get something from here, I think. And similarly, if I replace this f of b by f of b minus a, so yeah, and here also then I'll get f of phi plus f of a union b. And now if I take the addition of both the inequalities here, uh,
Okay.
then I will get what? Uh, so if I take summation here, so I'll get f of a plus f of b, yeah, uh, plus f of a plus f of b. This would be greater than or equals to the twice of this thing, f of a union b. And following this submodular property, this f of a plus f of b should be greater than this thing. No, 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 no. We have to think in terms of this. So f of a plus f of b, uh, clearly. So now this 2f, can we get something useful from here? So yeah,
Mm. We
so
have to
this,
get f intersection b somehow into the picture. We have
oh, I
two
see.
f union b. So we want to somehow get an f a intersection b. I think that is necessary. Uh, have almost everything in place except that A intersection B thing. Okay, so what we can do? Okay, so we can do something, right? See, here we are going to get rid of one A intersection B, and we will get from here. So because you're not able to see, making it slightly smaller, that is fine, right?
Visible, yeah, it's visible to me.
Okay. So if if A intersection B, A union B can be bounded from above by FA plus FB minus FA intersection B. Okay. From the original equation.
Yes.
So now one of this A intersection A union B we will replace by no. So we want this thing to be greater than. We want something greater than. We want F union B is. We want a lower bound on F union B so that we can replace F union B by something.
But in all these simplifications, we are not taking the benefit of this fact that f of x is equal to the f of Vg excluding x. We are not taking its
Okay.
benefit.
Okay, that's a good observation. Okay. So F of A minus B. What is the complement of F of A minus B? Complement would be B and everything else in the universe.
So what this f of x and this f of Vg, all the vertices excluding x, all the vertices excluding x.
Yes.
So all the vertices excluding x means what? I mean, vertices are either in A or in B and nowhere else.
No. Vertices could be outside of A and B also. So A and B are just subsets. For example, and here B could have been only C. So
Oh, I
A and
see.
B are subsets of the vertex set.
Okay. Fine. So yeah. So since we are working with symmetric F, so therefore this complement thing should make sense. So
Yes, we have to use this somehow. A union B complement and A intersection B complement are related to A minus B, right? Yes. So observe that the complement of F of A union B by using this symmetricness is F of A intersection B is, let us say, everything that is outside of A and B. So let us say mm, F of Bg minus A union B. Okay, so Vg minus A union B is what? Let us say Vg minus A and B is denoted by C. Okay, so everything that is not in A and B is C. Okay. Now f of A intersection B is f of C union B minus A union A minus B.
Yes.
Using the symmetric property.
Yes. Probably some very small thing is missing, which otherwise it is not difficult to see. So it says that the function value of A is the function value of the complement of A.
Yes.
So yeah,
So
must be
maybe I
some.
will just work it out. It is not
There must be
straightforward.
some. Yeah, some set theoretic identity might be there, which might be establishing the relationship in between its
Mhm.
set and its difference and its complement. Yeah.
So what is the deadline for this assignment? Just let me check the deadline. So if the deadline is imminent, then I will solve it and I'll post it on the group on the ask a question forum. But let me check. But week 9 is going on. Week 9 quiz 9 assignment. Uh, Opening. The due date is on 27th. So we are meeting next on 29th. Okay, so I will post an announcement in the course web page. Not announcement, in the ask a question in the forum, I will write a solution for this. I'll just work it out.
Yes. And so we have in the next week, what other topics? So which topic shall be covered in the next week? Uh, Metroids or this algebraic techniques? So which one shall be covered?
So in the videos, if I look at the videos, then week 10 videos are out. So algebraic techniques and uh, yeah, matrix multiplication, polynomial method, Hamiltonian path. I see that. So there are 4 examples of algebraic techniques: coloring, Hamiltonian path, matrix multiplication, and polynomial method. So the questions would be from these, and then I will discuss this question. So you have any specific question? I don't understand. So these are the 4 topics
No, no,
which.
yeah, no. As such, I do not have any specific questions. So because in the course homepage, a different order of the topics to be covered is given in
Oh,
the course because of
I
this.
did
So
check. I, so this is a course home page. So this is
uh,
week. We are in week 9 is completed.
not here. I mean, on the course homepage, I mean that when we go to the very first page,
Okay.
wherein the about the course is given. So and then
Okay.
the
Okay.
course layout is given. Yeah.
Let's open.
So if you just click on this parameterized algorithm link, then it will take you there.
It's not going there. Maybe it is here. Okay, it has gone to a different page.
So you'll have to go here to my course. Yes, my course pages. Inside your name and then your my courses here. And then you search for this parameterized. Go to the home page here. Go to course. But it takes you here and yeah, below this here, this one. Scroll, yeah, this one here. Yeah, it gives
Oh,
here.
no, this is wrong. So we are going by the a present run of the course where the videos are shared weekly. So in the weekly videos, if I see, we are going to talk about algebraic techniques. So what has happened is this week 8 important separators have been divided into 2 weeks now in this semester. So important separators is now spanning over week 8 and week 9, I think. So if you look at
Okay.
what we have seen in week 8, okay, so week 8 we have seen dynamic programming videos, and week 7 also we have seen. So earlier in week 9 these things were not there. So I think 8 and 9 were clubbed together earlier. Now they have broken 8 and 9. In fact, earlier week 9 didn't have anything. So now in week 10 we can see this algebraic techniques, 4 examples. So we are going to look at these videos and corresponding assignments next time.
Yes, yes. And there is a question in the chat.
Okay, I have doubts in last lecture of week 6 and also in graph imbalance problem for week 8's question. Okay. So yeah, so week 6 you have said before, but week 6 is a very, the last lecture has too many things. If you have any specific doubts, then you can ask me a specific doubt, then it will be easier to go through that. Because if I have to uh, revisit week 6 last lecture and talk about that, itself is going to take more than 1 hour. Imbalance problem, we can look at it. From week 8's content imbalance problem, we can look at it. That is simple. Specifically three coloring problem. So let's look at three coloring problem from uh, week 6 last lecture and imbalance problem uh, next time. So Course-Ellis theorem and this second order monadic, those things are not too comfortable. But these two we can look at next time, right? All right, okay. Okay, then thank you for joining. So let me stop the recording.
Thank you so much. And today's session was really good. We had lots
Yeah,
of discussion. Yeah, thank you.
yeah, that is.
Yeah, thanks. Bye, everyone.